So today you're going to use this lab in your lab, but we're going to be doing Kirchhoff's laws. So for double or three batteries. So when it's one battery, it's easier because we can construct a system of parallel and series resistors. When it's a two batteries or three batteries, then you have to resort to Kirchhoff's laws. So I'm going to do one now without needing Kirchhoff's laws. I'm just going to put a bunch of resistors, construct the circuit. Nice. It's already flowing. Okay, so then we can give this any voltage we want. Okay, let's say 24 volts. And we'll write down conventional current flow. So remember, it's actually electrons that are flowing the other way, but it has the same effect as protons seeming to flow this way, you see. Because when an electron leaves here and goes there, it's as if a proton went there, you see. So that's called conventional current. Let's see here, values. Okay, so this is 10 ohms. We can give each resistance something random. Okay, so then we're gonna, let's see here. We're gonna give this a tiny bit. When you guys do this in the lab, you'll give the wires a tiny bit of resistance to make the lab realistic. In other words, disconnecting wires. If you do zero resistance, then there's going to be no errors. So right now, to do an example, I'm just going to do zero resistance. But when you do it in the lab, you'll give the wires. So essentially, you're saying this wire in and of itself has slight resistance. This wire has slight resistance. So you'll give them a tiny bit of resistance. So if I make it zero, I'm also going to make the battery have no resistance. Okay, so 0 resistance for the battery, 0 resistance for the wire. Okay, now take the voltmeter, take the ammeter. If I place the ammeter here, I should be able to predict what the current is going to be. Where is the current? Oh, let's see here. Oh, to measure current, it's a little bit trickier. You have to break the circuit and you have to put it wherever you want it. Oh, there you go. Okay. So the ammeter, there's the current in this circuit is 0.75 amps. Now, voltage is easier to measure. You just put it across wherever you want it. You see? So since the current is flowing this way, this side is going to be at a higher voltage than this side, you see? So then the common, you put it at the lower voltage, and this one, the hot wire, you put it at the higher voltage, and it reads positive. If you did it the other way, it would read negative because you're putting the common at the higher voltage, and then you're putting the red, the hot wire on the lower voltage. So that's why it's reading negative. It's not wrong. It's just reading negative. So if you want it to read the positive, you do the opposite. So let's do this circuit together. Try to put them in combination of parallel and series. So you can see that these two are actually parallel. When I go from here to here, the voltage drop is the same as if I go this way, because this wire has no resistance. So the voltage drop this way and then this way is the same. So then this circuit would look like this. Essentially like that, R prime. And then we could say 1 over R prime is equal to 1 over 14 plus 1 over 6, right? And then that's going to be what? 6 plus 14, 20 over 84. And R prime equals 84 over 20. So remember, you reciprocate them at the end. And 4 goes into their 21 times. 4 goes into their 5 times. So it's what? 4.15 is a 2, right? 4.2 ohms. So the net of those, remember in parallel, the net resistance should come out less than either one. So the resistance is reduced. Now these two is pretty easy because it's just right away 30, the net resistance. So it acts as, we can just do that quickly. So that's 30, right? Then we can do, these two are in series. I mean, sorry, not a series, parallel. So we have here 1 over, so let's call this R double prime. Okay, so then you're going to have here 1 over R double prime equals going to be 1 over 30 plus 1 over whatever that was, which was 4.2, right? So then 1 over 4.2, what is that? So multiply, so 4.2 plus 30 over 3 times 42, it's going to be 626, right? So multiply them. It's going to be 42 times that. Yeah, 126. So that's going to be 34.2 over 126. Our double prime is 126 over 34.2. 3.68421. Okay, then I'm going to add that to that in series. And then get the total resistance, right? Our total is going to be, so 16 plus that. 16 plus that. And that's going to be what? 19.68421 ohms. Okay, so then we start going backwards, right? Then we say, oh, well, what's the current then here? 24 divided by 19.68421. $1.21925. So then that's going to be the current here. So it's going to be 1.2921925. 1.21925. And then once we find the current here, we can find the voltage there by multiplying it by our double prime, right? So 1.21. So then this 1.21925 times 3.68421. So then the voltage here is going to be 4.491978 volts. Okay, then you're going to argue that the voltage there and there are the same. 4.49, 4.49. Right? And then from there, what do we do? Oh, okay. If I know the voltage here, I can calculate the current here, right? The current here. So then the current here, let's just say I'm trying to check only these two things that the simulation had. Of course, the problem might ask you anything, but if I'm just trying to check these two, so I'm trying to get there as quickly as possible, right? So I'm trying to show that the current here is 0.75 and the voltage here is 1.5. So if I'm trying to get to that voltage, I want to go from the voltage of these two being 4.49 to calculate the current there, right? So the current is going to be what? 4.49 divided by 30, right? Divided by the resistance. So 4.49 divided by 30. So then the current here is going to be 0.14973. Right? Then I multiply that by the resistance of 10, and then there you have it. 1.497, yeah, very, very close, right? So then the resistance here, voltage of the resistance, 10 times 0.14973, 1.4973. Yes, yes, yes. So 1.50, nice. Okay, then how do I go to that current? Let's see here. What was the last thing that I had done? Oh, I knew that the voltage here was 4.49, right? So then I could divide that by R prime, which is this guy, and that will tell me the current here. Or hold on, is that the best thing to do? Because I'm trying to just check the current here. Was this the voltage? How did I get that? Okay. I knew the current here. I multiplied it by the resistance. I got the voltage. Then I argued these two voltages are the same. So then I went to this left side. Then I divided this by this. I got the current is 0.14, right? Then I multiplied that by 10 and I got 1.49. Now, if I want to go to the right side, I already know the voltage. I could divide that by the resistance to get the current. Or wait. Isn't it better if I know the voltage here? I think it's better if I'm trying to get to there as quickly as possible. It's better just to argue this voltage is the same as the voltage across these two, rather than calculate the current of this one. Yeah, that's a quicker way. Go directly by saying, oh, the voltage here is the same as voltage here and voltage here. So 4.49 volts, 4.49 volts. You see that? Then you can just divide that by the resistance and you get the current in that part. You see? So let me take that. So my current is going to be 4.491978 divided by, all the way up, and then divide that by 6. Yes. I theoretical is 0.749 amps. Good job to me, huh? So 3/4 of an amp. Yep.